Hi everyone. So now what we're going to do with this section is we're going to go on to finding the eigenvectors of a matrix. So we know that in section 2 we learned how to find the matrix, the eigenvalue of a matrix. So technically speaking, our goal literally here is what? For each, and to be more specific, for each eigenvalue I should have a corresponding eigenvector. So that's going to be our goal. Our goal is going to be to find the corresponding eigenvector to eigenvalues. So we're gonna define something in a minute where we'll go after that. So before we do that, from last section we kind of talked about this. So here's what we know. So we know that if V is an eigenvector with corresponding eigenvalue, and we talked about this in section 1 as well. This implies that AV equals to lambda V. And then in section 2 we said, well, this is equivalent to A minus lambda times I sub n V equals to the 0 vector, which if we look at this, see, we kind of show that this turns into that in section 2's notes. So what is it that we notice? If V is an eigenvector, then we notice that this is true. So what does that mean about V? V is in the kernel of A minus lambda times I sub n. So in other words, to find our eigenvectors that we're trying to look for in this section, this is implying, thus, we need to find the kernel of A minus lambda times I sub n, and that's what we're going after. So before we do that, let's define what an eigenspace is, which is going to basically go after the kernel, except we're going to notice that we're going to build off of that. So for definition 7.3.1, which is eigenspaces, and this says, consider an eigenvalue lambda of an n by n matrix A. Then the kernel of the matrix A minus lambda times I sub n is called the eigenspace associated with lambda. Denoted by E sub lambda equals to the kernel of A minus lambda I sub n. Okay, so what this means is that what we have here is for each lambda, our eigenspace is defined as the kernel of A minus lambda I sub n. Okay, so we're going to go after our eigenvectors after we find the associated eigenvalues, obviously, because we need to know these to be able to go after the eigenvectors. Okay, so in other words, what we're saying is this is the set of all vectors V in Rn such that AV equals to lambda v, and that's literally what we're going after, right? So when we do this, we're doing that, okay? But this is per eigenvalue. So once we find our eigenvalues, then we're going to go after the eigenvectors. So what we're going to say is that so the eigenvectors with eigenvalue of lambda are the non-zero vectors in the eigenspace E sub lambda. Okay, so that's literally what we're going after right now. So we're going to go after the eigenvectors for each lambda, and these are the vectors in each eigenspace of E sub lambda. So then the next question is going to be, well, once we do all of these and we find all of our eigenvalues for each eigenspace, then we'll get into the eigenbasis. But let's not go into that just yet. So let's go after finding our eigenvectors for each eigenvalue, or in other words, finding the eigenspaces. Okay, so let's look at an example where we're going to do that. So for example 1, we were saying find the eigenspace of the matrix A, which is 1, 2, 4, 3. Okay, so to find the eigenspaces of this matrix, the first thing we need to do is we need to find the eigenvalues. So find the eigenvalues. Okay, so if we're finding the eigenvalues, we know from section 2 that that's literally what? Just the determinant of 1 minus lambda, 2, 4, and 3 minus lambda. And then if we find the determinant of this, what is that? That's going to be 1 minus lambda times 3 minus lambda minus 8. And I'm finding I guess we're finding the characteristic polynomial, and then we'll set that equal to 0. So this breaks down to lambda squared minus 4 lambda, and then what will I get here? A plus 3 and a minus 8, which becomes a minus 5, and this factors to lambda minus 5 times lambda plus 1. Okay, so now that that factors, we could see that when I set this equal to 0, my eigenvalues here are going to be lambda sub 1 equals to 5, and lambda sub 2 equals to negative 1. Okay, so now that I have my eigenvalues, now I'm going to go after my eigenspaces here, right? So what's my eigenspace? My first eigenspace is going to be found with the eigenvalue of 5. So capital E sub 5, which is my eigenspace corresponding to eigenvalue of 5, that's literally what? The kernel of A minus 5 I sub 2, which ends up being what? The kernel of negative 4 to 4 negative 2. Okay, so literally that's A, and what am I doing here? If this is minus 5i sub 2, that's just going to be minus a diagonal matrix with 5s. So all I'm doing is what? Subtracting 5 from there and there. And if I do that, and these guys won't change. So it'll be negative 4, 2, 4, negative 2. So now what I want to do is I want to find the kernel of this. So through inspection, I think we can figure this out. That's actually pretty straightforward. Now remember, we could come up with more than one vector that works, except what will happen is, when I say more than one vector, is your vector might look different than mine, except we'll know for a fact that they have to be parallel to each other. But what do I notice here? these vectors are, this vector is half of that and it's the opposite of it. So the easiest way through inspection would be what? If I were to kind of, what vector could I find where it'll be in my kernel? Here's what I know. Well, if I grab this column and multiply it by 1, and if I grab this column and multiply it by 2, what do I notice then? They'll be exactly the same, they'll end up being the same vectors, which then if I combine them, it'll zero out. So what is it that I know here? The vector that I would need to multiply to this matrix to get the 0 vector would be 1, 2, right? So this was through inspection. Now, if you wanted to, you could have also done this the long way and see if it becomes more complicated through inspection. That's fine. There's nothing wrong with it. What you could have done is you could have said, the alternate way would have been, you would have said -4, 2, 4, -2. If I want to find a vector in the kernel, what does that mean? I'd have to multiply it by a vector where I get 0, 0 in return. And then you see that you could get a system of equations here, right? You'd get -4x plus 2y equals to 0. And what else? 4x minus 2y equals to 0. And then you could use a system of equations here to solve this and then find out what x and y need to be. But for some of the ones that are very easy by inspection, what do I notice? If I multiply this by 1 and multiply this by 2, then I know that I will end up getting the same, or the vectors that I need to zero things out. So what we notice is this implies what? My vector space, or my eigenspace for 5, for the eigenvalue 5, is what? The span of 1, 2. Okay, so what we notice here is, now we would say that we need to move on to the next find the next eigenspace. So for the eigenspace for -1 would be the kernel of A plus I sub 2. Now this became plus because obviously my eigenvalue was -1. And then what is that? That's equivalent to the kernel of 2, 2, 4, 4, like that. And what is it that we noticed? They're exactly the same. So what combination would I need to zero this out? Well, here's one way of thinking about this. I could multiply this column by 1, this one by -1, and then that would make them exact opposites. And then when I combine them, they'll zero out, right? So what we're noticing here is that this implies that my eigenspace for -1 is just the span of the vector 1, -1. And remember, we didn't have to say 1, -1. We could have said -1, 1. It doesn't matter, right? As long as we come up with a way where this column and that column would be exact opposites, that's how we know we'll be able to zero them out, right? So this is kind of like the vector that I'm trying to find that would get these guys to be exact opposites, so when I combine them, they zero each other out, right? That's literally what the kernel is, right? So technically speaking, these 1 and -1s, that's the vector here, right? I'm saying, look, 2 times 1 is 2, 2 times -1 is -2, when I add them, they zero out. 4 times 1 is 4, 4 times -1 is -4 plus -4, they zero out. So that's kind of what I'm doing up here. I'm just trying to see what could I multiply to each of these columns where they'll be exact opposites, if any, right? If it does exist, and in this case they do. So what we notice here is that we found our eigenvectors here. Now the easiest way to see if we did this correctly, obviously you would have to do what? You can check to see, for instance, AV equals to lambda V, which I'll leave that up to you to do, but we could see, for example, you can say grab your matrix A and then plug in 1, -1, so this is what we're claiming V is, or any linear combination of this, right, or any multiple of this equals to -1 times V. You'll see that you'll get the same thing. Okay, so now let's kind of make a comment on this before we move on. We could say that since A is is the space of all 2 by 2 matrices, and we have 2 linearly independent vectors. And what are the 2 linearly independent vectors? If you look at the eigenvector we had for this space, which was 1, -1, and then the eigenvector we found for the eigenspace of E sub 5 was what? It was 1, 2, and clearly 1, -1, and 1, 2, they are linearly independent. So we're actually noticing something, right? So this implies we have 1, 2, comma, 1, -1. See, these are clearly linearly independent. They form an eigenbasis for matrix A. Which, notice how, why is this an eigenbasis? Because look, we're in R2, and we know that to have a basis for R2 we would need 2 linearly independent vectors. So notice how these eigenspaces or these eigenvectors, I have 2 of them and they're linearly independent, so that's what an eigenbasis for A becomes, right? So this is a basis and it's just they're all eigenvectors, and if my eigenvectors form a basis, that's known as an eigenbasis. In fact, if we were to draw a visual representation of what we just found, see, what do we find? The eigenspace for the eigenvalue of 5 was what? It was the span of 1, 2, which would be any vector along this, right? So this is capital E sub 5, right? That's what we found. So any vector along that's parallel to this line would do. And then what was the other one? It was 1, -1, which is any vector here. And what do we notice about my eigenspaces? See, I have 2 vectors that are not parallel, right? Which would mean it would span all of R2. Therefore, it becomes an eigenbasis. So we know that this forms an eigenbasis for A, and we can even say that A is diagonalizable. Right? How come? Because what is it that we know? What would S be filled with? With S being filled with our eigenvectors, which would be V sub 1, V sub 2. And what do I know here? This is a square matrix, and we know these are all linearly independent. So clearly this is going to be invertible. And B would be filled with our eigenvalues on the main diagonal. Now, you just have to remember, though, keep in mind that if you look at the example that I did, lambda sub 1 and lambda sub 2, you need to be careful. You need to make sure that you match things up. So obviously V sub 1 and lambda sub 1 should match up. V sub 2 and lambda sub 2 should match up. So in other words, here's what I mean. If I put my eigenvalue -1 here, which was what I called my lambda sub 2, then I need to make sure that the eigenvector that I found for my eigenvalue of -1 has to be here, right? So for example, if I had called this, if my lambda sub 1 was -1, then what would that mean? 1, -1 would have to be in the first column. So just make sure that you stay consistent. That's all I'm saying, okay? So let's look at our second example. Find the eigenspace of matrix A, which is filled up with 1s along the first row and 1s along the third column, and then everything else is zeroed out. So the good news is here, if I want to find the determinant of A minus lambda I sub n, that should be pretty straightforward, because all it ends up being is what? 1 minus lambda, 1, 1, 0, minus lambda, 1, 0, 0, 1 minus lambda. And I'm going to go ahead and just give you what the characteristic polynomial becomes in factored form, which is literally just what? My main diagonal, right? Because this bottom entries are zeroed out, so we know that if it's a triangular, then my eigenvalues are just the main diagonal. So this is just going to be 1 minus lambda squared times negative lambda. So what I could call this is what? Then I could say lambda sub 1 is 1 and lambda sub 2 is 0. So I have two eigenvectors. Okay, so let's find the eigenspace for 0 first. And what does that give me? It's just literally the kernel of a minus 0I sub 2, which is just literally what? The kernel of a. And the kernel of a, which ends up being 1, 1, 1, 1, 1, 0, 0, 0, 0. And so what do I notice here? How could I zero this out? Well, what do I know here? I know that these two columns are exactly the same. This column, actually, there's no way I could use these zeros to get a negative 1 there. So what do I know here? This last column, I have to zero it out, right? Because if I don't zero out the last column, then I won't be able to get opposites. So I'm going to zero this out. Now, what do I notice about these guys? They're the same. So how do I get them to be the opposites? Well, one of my vectors has to be negative 1, or I want to multiply one of the columns by negative 1, the other one by 1. So notice how if I take negative 1, 1, 0, and I combine them, I'll get to the 0 vector. Now, is there another way around this? Well, someone might say, how about if we did 1, negative 1, 0? That's fine, except 1, negative 1, 0, and negative 1, 1, 0, they're parallel, so I can't use that, right? They're the same vector, pretty much, right? So there's no other way of forcing out another vector, a different vector that's not the same as this guy or parallel to this guy that would give me the 0 vector out of it. So in other words, what is it that we notice? The only thing we have is what? This implies we get the span of negative 1, 1, 0, right? That's my eigen space for E sub 0. Okay? Now, going on to finding the eigenspace for 1, what is it that we have here? We have the kernel of, and this should be a 3, of a minus I sub 3. And what does that give us? That gives us the kernel of, we want what matrix, what is this going to be? It'll be 0, 1, 1, 0, negative 1, 1, 0, 0, 0. And what do I notice about the last two columns here? Those two columns are literally what? They're linearly independent. Okay, and the first column is just literally all zeroed out. So what I'm saying is the first column we could multiply by anything. So let's just say we multiply this by 1. But since these two are linearly independent, what does that mean? I cannot grab these guys and multiply them by a constant to get them to be exact opposites. So the only way I could get rid of these is by zeroing them out. Now remember, as long as I come up with a vector that's not a 0 vector, that could be an eigenvector. And sure enough, since this column is filled up with zeros, we're okay with that. We can just say multiply this by any number. So I chose 1. You could multiply by anything, to be honest, except don't multiply by 0, because the 0 vector, we don't treat that as an eigenvector. Okay, so 1, 0, 0, that's our vector. That becomes the span of 1, 0, 0. And there isn't any other way that I could force out the 0 vector here. So what do we notice here? I'm in R3, but how many vectors did I find? How many eigenvectors did I find here? I found 2 of them. So what does that mean about matrix A? We don't have an eigenbasis, and therefore it's not diagonalizable. Remember how we kind of talked about that for the first example? So notice in this example, we would say matrix A is not diagonalizable since we have only 2 linearly independent eigenvectors. So we noticed that we found 1 in the eigenspace of E sub 0 and one in eigenspace of 1. So what we notice is obviously we don't have an eigenbasis, and if I write out my matrix S where we fill out with our eigenvectors, we'd notice that we wouldn't have a square matrix, and therefore we wouldn't be able to find its inverse, or it wouldn't be invertible, and so therefore we notice that A is not diagonalizable. Okay, so here's an example where we notice that my eigenvectors don't form an eigenbasis. Okay, so moving on to the next definition, which is tied to our geometric multiplicity. And I'll make a comment on geometric multiplicity. I know last section we talked about algebraic multiplicity, and clearly geometric multiplicity and algebraic multiplicity will not be the same thing. But first let's define what, or not necessarily, they may be the same, but we're not guaranteed. Okay, so let's talk about what a geometric multiplicity is. So we'd say consider an eigenvalue lambda of an n by n matrix A. So then we would say that the dimension of the eigenspace E sub lambda, which is literally what? All the vectors in the kernel of A minus lambda I sub n, right? So is called, so remember the dimension, if you think back to first semester, the dimension was literally how many vectors we had in our basis. And basically what we're doing here, the vectors that we have in our eigenspace is just all the vectors that are in the kernel of A minus lambda I sub n. So that's what we're going after. So this is called the geometric multiplicity of the eigenvalue lambda, denoted GEMU lambda. Okay, so just remember, how do we find the dimension of some space, or in this case the kernel of this? I need to find how many vectors are in the kernel of A minus lambda I sub n. So it's pretty much, that would be the dimension. It's kind of like find all the vectors that span the kernel of A minus lambda I sub n. And when you do that, then that's your geometric multiplicity. Okay, so we would also say that thus, using that understanding, we know that the geometric multiplicity of lambda is literally what? The nullity of A minus lambda times I sub n, which, remember, that's what the nullity is, the dimension of your kernel, which if you think back to it, that's the same thing as saying what? It's n minus, right? So if I have an n by n matrix, its dimension is n, but then what do I want? I want the dimension of the kernel. So what's the dimension of the matrix A? It's literally what? We want also to take away the rank of A minus lambda I sub n. Because remember, the rank is just all the leading ones. So when you take away the leading ones, we know that that's going to tell us what's not in our kernel. So when you subtract it from your entire dimension and you take away the dimension that's not in your kernel, then what you're left with is the dimension of your kernel. All right, so if you remember, we did talk about this first semester. So a comment I want to make here, which is going to be important: geometric multiplicity and algebraic multiplicity may be different. right? And if you think about it, it makes sense, because in our case right here, what is it? The algebraic multiplicity is just where that's literally giving you the count of each eigenvalue, where the geometric multiplicity is literally what? That's the dimension of our kernel. So there are two different things, right? So a perfect example would be the second example that we just did. For example, in example 2, what was it that we noticed? The geometric multiplicity for the eigenvalue 1 is what? The dimension of the eigenspace for the eigenvalue of 1, which that was what? We came up with only one vector. But if you think about it, when we found its eigenvalue, the algebraic multiplicity of 1, we noticed that we had a repeating root of an eigenvalue of 1. So our algebraic multiplicity was 2. So clearly we could see that they're not the same. Okay, so now let's move on to our next theorem, which will kind of talk about eigenbasis and geometric multiplicity, and it'll put them in, it'll kind of compare the two, and we'll start seeing a relationship between the two. So these are so we have the first part says consider an n by n matrix A. Okay, so if we find a basis of each eigenspace, which, if you notice, that's what we did in the first two examples, right? We found each eigenspace, and then we found all the eigenvectors that were linearly independent for that eigenspace. And in our examples, we were able to find only one, but there could be cases where there's more than one, right? And so we would have to find a basis for each eigenspace of A and concatenate all these bases. So all these bases. So it's saying, hey, find the basis of each eigenspace and then put them all together. Now, there's a reason why we want to do this, put this together, because if you remember in example 1, we did it, in example 2, we did it as well. Then the resulting eigenvectors v sub 1, let's say we go all the way to v sub s. So let's pretend we have s eigenvectors. What do we know about those eigenvectors? They will be linearly independent. So what we notice here, the good news here is that we get things that they're linearly independent. And if they're linearly independent, what does that mean? How many vectors would I have? Well, think about it this way. If I have an n by n matrix, S cannot be any larger than n, right? Because if these are all linearly independent, I could have at most n linearly independent. So for example 1, we had exactly 2 linearly independent vectors. And we were in R2, which that was the case. So we had no more than n vectors. Now in example 2, we were in R3, but we found 2 linearly independent. So what that means here is that this result implies that what? That S is less than or equal to n. Okay? And then what we would say in part B, which talks about diagonalizable, and I think that we already know, right? So matrix A is diagonalizable if and only if the geometric multiplicities of the eigenvalues add up to n. So if you think about it, what are we doing? We're grabbing part A, we're saying, look, S has to equal to n, right? That's literally what we're saying. Now, that makes sense, right? Because the geometric multiplicities, that's what, it's the dimension of each eigenspace, right? So if I add them all up, then what do I notice? If they add up to n, then what does that mean? The number of linearly independent vectors I have is the same as the space I'm in, or the dimension I'm in, and therefore it'll become, not only will it be my eigenvectors, it'll be an eigenbasis, and if it's an eigenbasis, then we know that it's diagonalizable, right? So it's kind of, there's a lot of nice things going on here, okay? So moving on to our next theorem, which this one says it has to do with n by n matrices. So an n by n matrix with n distinct eigenvalues. And hopefully you already have an idea with what's going to happen. So if I have an n by n matrix and all my eigenvalues are distinct, there should be something that we're guaranteed here, and I'll kind of go into it as well once I write out the theorem. But hopefully you already have a good idea as to what it is that we're going to get into. So if an n by n matrix A has n distinct eigenvalues, then A is diagonalizable. Hopefully you understand why that's the case. Because look, if I tell you I have like 5 is an eigenvalue of my matrix A, then what does that mean? There has to be an eigenvector. So it's impossible for us to have an eigenvalue where there is no eigenvector, because we know that by definition, if we have an eigenvalue, there has to be an associated eigenvector that ties itself to the eigenvalue. So if I have n distinct eigenvalues, then I should have, for each eigenvalue, I should have an eigenvector, right? And if I have an eigenvector, then that means I should have n eigenvectors. And if I have n eigenvectors, then that means, and this is an n by n matrix, then that means by theorem 7.3.3, A should definitely be diagonalizable. So it's, when is it that we may lose eigenvectors? It's when I have an algebraic multiplicity of greater than 1, or if not all my eigenvalues are distinct. So that's the only time where you'd have to be careful and say, well, maybe my matrix isn't diagonalizable if I don't have n distinct eigenvalues. So that's when we'd have to kind of check and make sure. So then we can easily then construct an eigenbasis by finding an eigenvector for each eigenvalue. Right? Because if I find an eigenvector for each eigenvalue, then I could put them all together, and then that will be my eigenbasis, right? Because then we know that they're all going to be linearly independent. Okay? So moving on to our next example. So for example 3, is matrix A equal to, which is 1, 2, 3, 4, 5, 6, 0, 2, 3, 4, 5, 6, 0, 0, 3, 4, 0, 0, 0, 4, 5, 6, 0, 0, 0, 0, 5, 6, and 0, 0, 6. So the question is this diagonalizable? Well, I guess the question here becomes, we're not being asked to diagonalize A, so hopefully you're not going through the process of trying to find all the vectors or all the eigenvalues, all the vectors, eigenvectors, and so on. Even though finding the eigenvalues of this is very straightforward and simple, but we don't need to diagonalize. It's just asking if it is diagonalizable. So what could we use? Well, we just had a theorem that said, hey, look, see, this is a 6 by 6 matrix. So if I have 6 distinct eigenvalues, then I know that I'll have 6 eigenvectors, which will make this diagonalizable. But we don't need to go out looking for the eigenvectors. We're just saying yes or no. And what is it that we notice? And the good news is, this is it's a triangular matrix, right? And what is it that we know about triangular matrices? When you find the eigenvalues, it's just the diagonal entries. So the good news here is that since the determinant of A minus lambda I sub 6 equals to 0, and what do I notice here? 1, 2, my eigenvalues are going to be literally what? 1, 2, 3, 4, 5, 6. But who cares about the values? What's more important is that this has 6 distinct eigenvalues. This implies it's diagonalizable. So the answer to this is yes. Now, if one of these was, let's say, also like not a 3, it was a 2, then the answer wouldn't be so straightforward, right? Then we would have to kind of go looking for it and see, hey, is this diagonalizable, yes or no? But we know for a fact that since they're all distinct, we don't need to go any further, and we could say the answer is yes to that. Okay, so moving on to our next theorem. So the eigenvalues of similar matrices. Okay, so let's go through this theorem and then we'll prove a part of it. The other parts will be pretty straightforward. We could kind of talk through like we did on the earlier theorems. So suppose matrix A is similar to matrix B. Then we can say that matrices A and B have the same characteristic polynomials. Okay, so what are we basically saying? If A and B are similar, then if you were to find the characteristic polynomial of A and you found the characteristic polynomial of B, you would notice that they're exactly the same thing. Okay, and then the rank of A would equal to the rank of B, and the nullity of A would equal to the nullity of B. And all this kind of ties down to one another. We could see why their ranks would be the same, because if they have the same characteristic polynomials, then what is that going to mean? They're going to have the same eigenvalues, and then in turn their eigenvectors, you'll have the same number of eigenvectors, so then we'll notice that their dimensions and the ranks and nullities will match up. Okay, so for part C, matrices A and B have the same eigenvalues And why would they have the same eigenvalues? Well, it all comes back to part A, right? If they have the same characteristic polynomial, then their eigenvalues should be the same. And then what we notice is, well, if that's the case, then they'll also have the same algebraic and geometric multiplicities. Okay. So one comment I want to make here is that however, their eigenvectors don't need to be the same. Hopefully you understand why, right? Because when we say matrix A and B are similar, we're not saying they're exactly the same matrix, right? It's just they have that property that AS equals to SB. So the number of eigenvectors will be the same, but the eigenvectors themselves do not necessarily need to be the same. Okay, but that's not what we care about if the eigenvectors are the same or not, right? It's just when we talk about rank and nullity and so on, we care about the number of vectors or the number of eigenvectors, which that's more important. So as long as I don't lose, which the geometric multiplicity is what we care about, that's where we notice that we care about the count of the eigenvectors rather than, hey, are they the same or not? Okay, and then for part D, matrices A and B have the same determinant and trace. So once again, we're saying that the determinant of A equals to the determinant of B, and the trace of A is equal to the trace of B. Now, hopefully we know why. See, everything once again falls back to part A. If they have the same if their characteristic polynomials are exactly the same, what did we learn earlier on in this chapter? That the determinant of A is literally what? One way of finding the determinant of A is the product of all its eigenvalues. Well, then guess what? How do I find the determinant of B? It's the product of its eigenvalues. And if they have the same characteristic polynomial, their eigenvalues are the same. So therefore, we could see that clearly their determinants will be the same. And same thing with the trace, right? Because the trace of A and the trace of B is just the sum of the eigenvalues. And since we know that their eigenvalues are going to be the same, then the sum of the eigenvalues will be the same. So the trace of A and trace of B is the same. So what I want to do is I don't want to just kind of wave my hand over these and say, hey, just accept it, let's move forward with it. But I think proving part A is the important one. And I could leave B, C, and D for you to kind of prove on your own. But I think once we show part A, everything will fall into place, because these are all kind of saying the same thing as part A in a different way, right? Or we would use part A to kind of show that these are also true. So let's prove part A. And then obviously if you have questions on any of these, don't hesitate to reach out to me. I'll be more than happy to answer any further questions you may have. But let's prove part A. So what is it that we're starting off with in part A? We know that matrix A and B are what? Or for all of these, what is our hypothesis? It's A is similar to B. So if I come back here and say, well, if A is similar to B, what is it that we know? We know that B is the same thing as S inverse AS. Okay? If you remember, we had AS equals to SB, and then S has to be an invertible matrix, so you just multiply by S inverse of both sides. And this is clearly true, right? We know that this is a fact. So here's how we're going to show that my characteristic polynomials are the same. So this implies the characteristic polynomial of F is literally found how? It's the determinant of B minus lambda times I sub n. Okay? So that's how we find the characteristic polynomial, right? Nothing new here. But what I know now is what? B is the same thing as S inverse AS. So this is equivalent to what? The determinant of S inverse AS times lambda I sub n. Okay, so all I did was I substituted. And then what we can do is, well, we can now say this is equal to the determinant of S inverse A minus lambda I sub n S. Okay, now what happened from here to here? Let me just point something out. All I did was I said, look, this we can think of it as what? The same thing as S inverse S, right? Because what do I know? A matrix, when you multiply a matrix and its inverse together, you get the identity matrix. And so I just said, hey, if I rewrite this as lambda times S inverse times S, then when I factor it out of this form, like this, that's still equivalent. Now, why is this important? Why did I care to do that? Because now think back to last chapter as far as determinants went. I know that the product of matrices, which these are all three matrices, the determinant of that, I could find the determinant of each of these matrices separately and then multiply them. So by definition, this is the same thing as what? The determinant, or I shouldn't say by definition, from last chapter, we know that that's the same thing as this. Okay? And then what else is it that we know? I could regroup these because after all they are scalars now. And then we're also going to use another fact from last chapter, which is what? What do we know about the determinant of S inverse? This is the same thing as what? 1 over the determinant of S. If you remember, we proved that last chapter. So if this is the same thing as 1 over the determinant of S times the determinant of S, that's going to become 1. And what am I left with? The determinant of A minus, which, see, this is so cool because what did I end up with? The determinant of A minus lambda times I sub n, which, what is that? That's the characteristic polynomial of A. So that's F sub A of lambda. And that completes our proof, right? So a lot of interesting things going on here, but I felt like from this theorem, the important one to prove was part A, because then we can kind of use the idea of A to make sense of B, C, and D, okay? So, and I would recommend that you guys do try to work on B, C, and D and try to prove that on your own and see if you can get through it, okay? So, let's look at our next example, which I believe this is example number 4. So for example 4, we're going to say the following. Is the matrix A, which is 1, 2, 0, 3, similar to matrix B, which is 3, 0, 1, 2. Okay, so there's so many ways of answering this question, right? I'm sure if you were to pause this and solve it your own way, you might get to the solution and the correct solution using a different method. But for me, the easiest way around it is looking at the trace, right? So I would say, actually, what do I notice? 1 plus 3 is 4, 3 plus 2 is 5. So clearly they're not similar because in the last theorem, we know that their traces must be the same. So the answer here is no, since the trace of A is equal to 4 and the trace of B is equal to 5. So clearly the trace of A does not equal to the trace of B. And we know that if they are similar, their traces must match up, right? Because their eigenvalues need to be the same for their characteristic polynomial, right? So, I mean, you could have even found their characteristic polynomial and shown that they're not the same, right? It's just there's so many ways you can do this. So the last thing I want to talk about before we wrap this up is algebraic versus geometric multiplicity. So, and this is just telling you about, we're going to compare the number as far as the number of algebraic and geometric. So if lambda is an eigenvalue of a square matrix A, then the geometric multiplicity of lambda is less than or equal to the algebraic multiplicity of lambda, which makes sense, right? Because what is it that we're saying here? And in fact, one of the examples that we did, we noticed that, hey, my algebraic multiplicity was 2, but my geometric multiplicity for that eigenvalue was 1. So what we're saying here is that our geometric multiplicity cannot be any larger than the algebraic multiplicity, because what is it that we know? For each eigenvalue, we're guaranteed to have an eigenvector. So if I have an eigenvalue that has a multiplicity of greater than 1, then what does that mean? I may potentially have more than one eigenvector for that eigenvalue, but I cannot have more than that. So we can see why that works the way it does. So we know that the geometric multiplicity of any eigenvalue can never be greater than its algebraic multiplicity. It just wouldn't make sense if that were the case. Okay, so that pretty much takes up this section, takes care of this section, and takes care of the chapter, in fact. What I would recommend is that the book, somewhere in the end of section 3, has a strategy for diagonalization. So I'm not going to write out that strategy. I think it would be important for you to look into it. But I think we already have a good idea of how to diagonalize, which is tied to the eigenvectors. But I would definitely recommend that you look into the theorem that talks about a strategy for diagonalizing a matrix. Okay, so that takes care of this section. Once again, if you have any questions, don't hesitate to email me. I'll be more than happy to answer any questions you may have, and we'll go from there.